Let's just start solving problem number 2 of homework number 2. In this problem, we have a space to be heated and humidified. The space has a calculated heating load of 125,000 BTU per hour sensible and 53,570 BTU per hour related. So I'm going to show my space like this. My space. So Q sensible of 125,000, and the unit is BTU per hour, and Q latent of 53,570, same unit. The steam with air enthalpy of 1150 BTU per pound is to be used to humidify the air. Supply air temperature into the space is 100. That is my supply. This is 110 F. Okay. The space is to be maintained at 75 Fahrenheit, 50% RH. So we show the temperature and relative humidity of this space on the return line. So if this is my return line, I show 75 Fahrenheit and 50% relative humidity on the return. So I know I have the two pieces of information for my return, so I can fix it on the side chart. For the supply, I only have one piece of information, temperature. Okay. This space is to be maintained at this condition. Ventilation air, which is nothing but outside air, in the amount of 1000 CFM is needed. And the outside air condition is also given. So this is what I have. I have a furnace. So this part, first part is furnace. And this is my humidifier. Let's show that A is separating furnace from my humidifier, okay? So for humidifier, I'm using a steam at enthalpy of 1150 BTU per pound mass. And for furnace, it's totally separated from the humidifier. And of course, air comes in from outside air, some part of it. So let's show the outside air with OA, and it's very cold, 35 Fahrenheit. And 60% RH. And my return air get exhausted, but some part of it is returned back to be mixed with, so this is still your return air, and notice here, this is my mixing to be mixed with outside air. So on the side chart, I'll show you how to show the mixing condition here. So it looks like this is all I have. Let me connect this supply line to my humidifier. And of course, I can show that this furnace gets some heat from either electric or natural gas or other sources. So let's call it Q furnace. That in section B, we're going to find out the heating capacity of the furnace in BTU per hour. So we're going to find out that Q later. Okay. So one quick note here is that the line going through this space from supply to return is called condition line. on the psych chart. In order to show it, I need to know the two pieces of information of each point. For return, I have it, so I can show it. On supply, for the supply, I only have one piece of information. So what I need to do is, remember, we have to use the SHF, sensible heat factor, slope, and which that slope is along the condition line of the space. So let's show our condition on the psych chart. Let's start with return air. Return, I have a fixed information of 75 Fahrenheit, 50% RH. So let's zoom in a little bit. So if I use the return information, 75, 50% RH. So this is my dry bulb line, horizontal, and 50% this is my relative humidity, where the point that these two are intersect are here. So that's my return air, right? For supply, I only have 110 temperature, which means that my point is along this 110 line. Somewhere along this 110, but I need another information such as humidity or enthalpy or another information to fix it. How I can find that? I'm going to use the sensible heat factor. So let's find out what is the sensible heat factor, which is nothing but sensible heat of the space over total heat, which is summation of sensible heat and latent heat, right? So my sensible heat factor is 125,000 BTU per hour over a total of 125,000 plus 53,570 gives me, I believe, 198,570. If you do this, you get a 0.7 for sensible heat factor. What that means is when you use the protractor tool of the psych chart, the inner numbers are showing the SHF, sensible heat factor. And here is I have 0.5, 0.6, and then jumps to 0.8. So in the middle, I have 0.7. So this is my 0.7, right? If I connect a line to 0.7, I'll probably do it with my line tool here. So if this is 0.7 to the extent I can do. So this is my SHF. This is my SHF 0.7 line. What that means is the condition line, which is the line from return to supply, should have the parallel slope, should have the same slope as this. So what I need to do is have a similar line and basically try to connect these two. If I kind of use the tool I have, let me see. Let me show my line kind of parallel to this line. This is not bad. So it looks like this is a good. I'm going to get rid of this line and this line. So here, I believe, is my supply. I'll probably need this space later. So let me just show supply with an S here. This is my supply. Again, why? Because the slope of this line is the same as the slope of this line. These two lines are parallel. This is how I can fix my supply condition by knowing 110 And the other information to fix it is the same slope. So this line is called condition line. And condition line go through the space from supply to return, as you can see, and it's parallel to SHF that we kind of calculated here. So perfect so far. Now, using this information, we can getting some information out. Let's also show the outside air. I have the information of 35 Fahrenheit, 60% RH. So let's see if I can find 35 down here and 60% RH. Here, this is my 60%, as you can see here. So if I follow this line, this curve all the way, this is where they intersect. So this is my outside air, okay? And I know my outside air connects to my return air in their mix, right? So let's connect it through a line. This is how my return air and outside air are mixed. And somewhere on this line that you're gonna find out where, is it in the middle or closer to outdoor air, outside air, or closer to the return air, I'm gonna show my M, which is my mixing point here. Because my outdoor air and return are mixed here, right? I need to find a condition of this location. So in the first step, now I think I have enough information to take it from here. Let's go ahead answer question part A, the amount of supply air needed to the space. So I'm going to find out the m dot of the supply air. To do this, so let's do the part A. To do this, I know that my Q total is equal to, so my Q dot total is equal to m dot supply air for SA for supply air times enthalpy of the return. So let's call it RA minus enthalpy of supply, right? Now let's go ahead and find those enthalpy on this chart here. We know that enthalpy lines are along these constant enthalpy lines. So for example, on this supply, I can show that if I follow my supply line here, along this, if I do my job well, I have a number close to 40. So let's call it a little bit over 40, 44 I. This is for enthalpy of supply. And for return, if I kind of go along these constant lines of enthalpy, I have perhaps 28.2 for enthalpy of my return air. So let's use these two numbers in our calculation to get the, oh, sorry, over here, to get the enthalpy numbers. So Q total is 178. So sorry, when I said 198 here, that should be 178. Looks like my note was bad. So this is 178. So Q total is 178, 570. So again, 178 comes from 125,000 BTU per hour of sensible plus 53,570, I believe. Yes. That is 178. Yes, so let me fix it completely. There you go. So still this 0.7 is correct because I was following my notes. So I'm looking for m dot supply here. Back into problem part A. So my return air and my supply air. So I start with my supply air here. So let's go with supply minus return. My supply air is 40.1. I just showed it on the side chart. Minus my return air is 28.2. So if you do this calculation, you get the m dot supply air of 15,000.6, and that's pound mass of dry air per hour. And by the way, for supply air, we'll see that on the side chart, we can find the specific volume of it, the specific volume of supply air. Let's zoom in. And these are my constant specific volume lines. So this is like 15.0. This is 14.0. So this is 14.5. So here I have somewhere close to 14.64. Okay. So I get 14.64 for my specific volume, which is cubic foot per pound of dry air. Okay. So using this, you can, now that you have the mass dot, m dot, and you have the specific volume, you can find the CFM of the supply air, and that's equal to m dot, which is 15,006 times the specific volume, which is 14.64 over 60, and I get 3661 CFM. I get 30,000 661 CFM. So that's for part A. Now let's go ahead and do part B. To find the heating capacity of the furnace for part B, let's go ahead first, find out the mass flow rate of the outside air. So let's go ahead and solve part B. In order to find the m dot of outdoor air, I know that I have 1,000 CFM, cubic foot per minute. And on the side chart, I can find is a specific volume, 12.52. I'll show you. And I multiplied this by 60 to convert from minute to hour. So 12.52 cubic foot per pound mass, I have a number of 4,792 pound mass per hour. If you're asking, okay, how we find this 12.52 for a specific volume of outside air, I need to zoom in. And remember, these lines are constant, a specific volume. And as you can see, we are very close to this 12.5, a little bit over 12.5. So 12.52, a specific volume is really coming from this line, right? So that's my specific volume. Now that I have the m dot for the air, remember I have outside air mixed with return air, and I had my supply air right into the furnace. And over here I have my mixing. So in order to find where we are, I'm going to compare the mixing conditions. So I know that 4,792 is from the outside. I still don't know about my return air, but I know my total supply is 15,006, right? We have found it in the calculation over here. So easily 15,006 minus 4,792 gives me how much m dot coming from the return. So I can go ahead and quickly solve for that part. That m dot of return air is nothing but total supply minus the outdoor air, 4,792. So my return air mass flow rate is 214 pound mass per hour. So I can easily say that my return air is more than twice of my outdoor air, right? So 10,214. In order to show it on the Psych chart, I need to show the fraction of the supply air coming from what source. Basically, all I'm saying is that if my total supply air is 15,006, what a fraction of it coming from return? So 10,214 over 15,006, that gives me 0.681, or 68% of my supply air coming from my return air, and again remaining coming from my outdoor. So basically all I'm saying is that on my Psych chart, if this line is connecting my outdoor to return, that and then mixing happens somewhere on the line, if the mixing ratio was 50%, it was exactly on the middle. Now that we are at 68%, and I know return air is more in terms of mass flow rate contributing to the supply rather than outdoor, so my 68% is closer to return air. So now I need to use a ruler to measure this line, and 68% from the outdoor air is, if this is almost 68 to the remaining, then my mixing would happen around here. So let's call it here. So let's assume this is my mixing. Okay. Again, this is the 68%. This is my remaining 20, remaining 32%, right? So if I have basically, I need to measure this line, probably 6 inches, for example, and 68% of 6 inches, this distance, and remaining is this. So this is how I show my mixing. So in the bottom line, in a summary, mixing location is closer to the point with the higher mass flow rate. Anyway, so now that I have it, I can find the mixing point information. And I know my mixing is happening at 60, a little bit over 60, less than 65. Again, if I do a better job, so 62 Fahrenheit is the temperature of my mixing, and relative humidity bias is on the 60%. So 60% RH. So let's write them down. So from the psych chart now, my mixed air has this 62-degree Fahrenheit dry bulb, 60% RH, and of course, I can find the enthalpy of my return air that I will use, and W of return air that I will use in next section. So enthalpy of my return air is, I know it's 28, is 20. Is this number here? So here I'm going to find the enthalpy of mixed air. As you can see here, I can find the mixed air location, go along the constant enthalpy line, and basically read the same way I did before. Enthalpy of mixed air, let's try it with MA. I show it on this left side of it, which is equal to around 22.6. How about the humidity ratio? I just go constantly to the right. Somewhere here, if you zoom in, you get the W of mixed air equal to 0.0071. Sorry. Okay. So 0.00 between 6 and 8, so that's what I picked, 7.1. So make sure this is 7.1. So another thing I'm going to show is that now that I know my mixed air location, so going back here, now that I know my mixed air, I'm going to show point A on the side chart. How? I'm going to go horizontal to the left, to the right from mixed location, because I know I'm on the constant humidity ratio line, because I'm just adding heat by furnace. So I go all the way to the A, and then from point A to supply, I'm just adding humidity. So I'm basically going along the vertical line up. And of course, we're adding humidity because it's warm already. We are adding, it has a higher enthalpy. We're giving probably some more dry bulb temperature as well, but it's mostly from A to S, expect some kind of vertical line going up. So now let's show from mixing point to A and then to supply on the side chart. So here again, I know that if I go from mixing point on a constant enthalpy line, somewhere here on this line, my point A should be, and then that would be connected to my point S. Again, I need another piece of information to make sure is it really going to be vertical down or has some slope. To do that, I'm going to still go ahead and use the psych chart protractor tool. Now this time I'm going to find out what's the delta of enthalpy over delta of humidity ratio. Find that ratio and basically solving that. So in order to find this, let's go ahead find the delta H over delta I. So in order to find delta H over delta W, so we can show it on the protractor tool. I know that for adiabatic humidification, delta H over delta W is equal to the enthalpy of the water injected, right? From the lecture notes. And we kind of drive the equation for this. So, and enthalpy, so this is for adiabatic humidification. And I know my enthalpy of the steam water into this was 1150 BTU per pound. So how I'm going to use it, I am trying to show 1150 for delta H over delta W using this protractor tool. Let's pick another color here, orange. This is 1000. This is 1500. So 1150 is 1100. This is 1200. Somewhere here. So let me do it again. 1050 is this. I can do a good job. So this is basically my, sorry. How can I get this collapse? Maybe, nope. Sorry. This is my 1050, which is equal to my delta H over delta W. This line should be parallel to the air supply to A line, which is almost vertical, right? But has some slope, it's not going to zero. So this is my point A. Now that I have my point A, I can find the enthalpy of point A. The line becomes an enthalpy line. Let's call it a little less than 35, so this is 34. It's the enthalpy of point A, and remember point A is the point between the furnace and humidifier. So now that I have the enthalpy of the point A, I can go ahead, calculate Q of the furnace. Equal to m dot of the supply air, 15,006, times delta of the enthalpy of 34 for my point A minus 22.6. That should be for my mix return, my mixing into the furnace. This will gives me 171,068 BTU per hour as my capacity of the furnace needed. And for part D, for part C, I need to find out the mass flow rate of the water for humidification. And that's also equal to the m dot supply times humidity ratio difference across the humidifier. So my supply 0.0124 minus my kind of mixing point, which is 0.0071. So this is coming from my supply, and this is coming from my mixing point W. And how we can find these W's? Just by going horizontal to the right and reading on the vertical axis. That gives me 79.53 pound mass per hour. So before I finish this, let me go back one more time on the psych chart here. So quick review. I started from my return air fixed condition. I had my supply temperature, but in order to fix it, I have drawn a line parallel to SHF. So I fixed my supply, and I had my outdoor air condition. I showed my line that my mixing happened along this line. And I showed that my mixing happened 68% far from the less mass flow rate income, which was mass flow incoming flow, which was outdoor air. So from this way, I show my mixing point. For mixing point, I separate my furnace from my humidifier. So I go horizontal to the right on a constant W line, and somewhere along this line is my point A. To find point A, I need to find delta H over delta W line, which is nothing but enthalpy of water injected, 1150, and parallel to this delta H over delta W, I show my SA line parallel to this. So this way I fix my point A, and I get some of the information from point A to calculate the capacity of the furnace, and on the last part, mass flow rate of the water needed.